95 degrees Fahrenheit. That is the number on every climate risk assessment, every IPCC report, every emergency plan designed to protect you from unsurvivable heat. It has shaped policy for 15 years. And nobody, not a single research team on Earth, had ever tested it on an actual human being. When Penn State finally did, they found the real number is 4 degrees lower. That is not a rounding error. 4 degrees, on the wet bulb scale, is the distance between a system that can protect you and a system that has already failed. And the conditions that exceed the real threshold are not projected for mid-century. They are being recorded right now on the Gulf Coast, where 35 million people live behind a power grid that just received a D+. If the idea that your body has a built-in temperature ceiling, a point where sweat stops working and biology starts losing, got you locked in, take a second and hit subscribe to Orbital View. We are tracking the wet bulb data through the entire summer across the Gulf Coast and Deep South. Drop a comment and tell me, do you know your county's heat action plan? I read every one. Here's what this investigation covers. A survivability number that governments and emergency planners have been using for 15 years, and the Penn State lab data that proves it is dangerously wrong. A Gulf of Mexico that is running hotter right now than at any point in the modern record. A Texas power grid bracing for demand that would have been unthinkable 5 years ago. And the compound event nobody is modeling. The one where the heat and the blackout arrive together. Let's get into it. Part 1. The lid. Right now, as you are hearing this, the National Oceanic and Atmospheric Administration's Climate Prediction Center has 36 states shaded for above normal temperatures this summer. Not scattered pockets, not a regional anomaly. 36 states. Only Wisconsin and Michigan do not have at least some portion flagged for extra heat. And the reason the forecast map looks like that connects directly to 2 things I need you to hold together for the next 2 hours. The first is El Niño. The International Research Institute's April models put the probability of El Niño conditions being present this summer between 85 and 94%. The European Center and NOAA both peg the chance of a strong event at 80%. That number climbed from 62% in the earlier assessment. It did not inch up. It jumped. And the IRI is not the only modeling center flagging this. ECMWF's latest coupled ocean atmosphere runs show some ensemble members tracking toward a strong event. The kind that reshapes global atmospheric circulation for an entire calendar year. If that plays out, late 2026 and especially 2027 could see global temperature records fall again. Weather Nation's analysis noted that the burgeoning El Niño could be very strong through much of the second half of 2026. The kind of language forecasters use when the model consensus is not just leaning in one direction, but converging on it. For the Gulf Coast, El Niño's relevance is not abstract. El Niño events correlate with enhanced ridging over the southern tier of the United States. Persistent high pressure that is the atmospheric precondition for heat domes. A strong El Niño summer means a higher probability of the kind of stalled, multi-week heat dome that loads the atmosphere with moisture, suppresses rain, and pushes wet bulb temperatures toward the thresholds this investigation is tracking. The signal in the forecast maps is clear. What remains uncertain is the magnitude. The second is the Gulf of Mexico. As of May 11, 2026, sea surface temperatures in the Gulf were tied with May 11, 2024, for the warmest on record for that date. Simple. And let me be specific about what warming means here, because the trend line is not gentle. The long-term warming rate from 1850 to 2025 is 0.03 of a degree Celsius per decade. Over the past 30 years, that rate increased by a factor of $10 to 0.32 of a degree per decade. Since 2012, it has accelerated again, by a factor of 16. Kim Wood at the University of Arizona has been tracking these numbers, and they are not subtle. So picture this. You have an ocean basin, a relatively shallow semi-enclosed body of water that acts like a thermal battery running at or near record temperatures. You have an El Niño loading the dice toward a hotter summer baseline across nearly the entire country. And sitting between that ocean and the atmosphere is a weather pattern that meteorologists call a heat dome. Think of it as a lid on a pot of water, A heat dome is a persistent ridge of high pressure that traps the air beneath it. It suppresses convection, kills the clouds and storms that would normally vent the heat upward. It compresses the air column, which warms it further through a process you can feel in a bicycle pump. Compress air, and it heats up. And it stalls. The dome does not move. It parks. For days. Sometimes weeks. And this is not abstract. In May of 2025, late spring, not even summer, a heat dome built over the Gulf of Mexico and brought a week of unusual heat and humidity to every state from Texas to Florida. The Washington Post described it as an early season lid that suppressed clouds, warmed the atmosphere vertically, and pushed parts of Texas past 90 degrees for more than 2 weeks straight. That event also warmed the Gulf surface water further, feeding the thermal cycle. The dome heats the air. The air heats the water. The water feeds moisture back into the dome. It is a feedback loop that tightens with each passing day. In July of 2025, the pattern repeated, bigger, hotter, longer. A lingering heat dome over the eastern half of the country put nearly 150 million people at major or extreme risk of heat effects over the course of a single week. Brian Jackson, a meteorologist at the NWS Weather Prediction Center in College Park, Maryland, described it as pretty notable for midsummer, a careful understatement from a forecaster whose job is to calibrate his language precisely. But here's the part that most coverage of heat domes leaves out. It is not just the temperature under the lid that matters. It is the moisture. When your lid is sitting on top of the Gulf of Mexico, on top of water that is running hotter than at any point in the observational record, the air beneath that lid is not just hot. It is saturated. The Gulf is evaporating into the trapped air mass continuously around the clock, feeding it moisture that has nowhere to go because the dome is blocking the atmospheric ventilation that would normally carry it away. And saturated air changes the equation from uncomfortable to biologically dangerous in ways that the standard temperature forecast on your phone does not capture. Because the standard forecast tells you the air temperature, it does not tell you whether your body can still cool itself. I spent the last 3 weeks inside the peer-reviewed literature on a metric called wet bulb temperature. It is not new. Climate scientists have been tracking it for decades. But the gap between what the science says and what the emergency planning assumes is, as of right now, wider than it has ever been. And the geography where that gap is widest, the Gulf Coast, the Deep South, the arc from Brownsville to Pensacola, is home to tens of millions of people whose emergency plans, building codes, and power grid were designed for a climate that the data says no longer exists. That is what this investigation is about. Part 2, the number everyone knows is wrong. In 2010, 2 climate scientists, Stephen Sherwood at the University of New South Wales and Matthew Huber at Purdue, published a paper that became one of the most cited findings in modern climate science. They proposed that 35 degrees Celsius wet bulb temperature, 95 degrees Fahrenheit, represents the upper limit of human survivability. Beyond that threshold, the human body becomes what physicists call an adiabatic system. It can no longer shed heat to its environment. Core temperature rises. Organs fail. Death follows within roughly 6 hours. The number was elegant, it was grounded in thermodynamic principles, and it became canonical almost immediately. The IPCC used it in its assessment reports. Climate models used it to project when and where the world would become uninhabitable. Risk assessments built their timelines around it. Emergency planners in Phoenix, in Houston, in New Delhi calibrated their heat action plans against it. When researchers drew maps of future habitability, the 35-degree line was the bright red boundary marking the edge of the livable world. That number shaped policy for 15 years. It shaped insurance models. It shaped military doctrine. The United States Marine Corps declares black flag weather and halts all non-essential outdoor activity at a wet bulb globe. Temperature of 32 degrees Celsius, 90 degrees Fahrenheit, a full 3 degrees below the Sherwood-Huber limit. It shaped the World Bank's assessments of which regions would remain economically viable under different warming scenarios. When officials in Abu Dhabi or Doha or Mumbai needed a number to anchor their climate adaptation strategies. They reached for 35 degrees the way an engineer reaches for the load-bearing capacity of steel. It was a constant. It was reliable. It was the foundation. And there was a problem with it that I have to be honest about, because it is the hinge this entire investigation turns on. Nobody had ever tested it on an actual human being. The number was derived from theory, from thermodynamic modeling. And the assumptions built into that model were so specific, so idealized, that they describe a person who does not exist in any real emergency. The model assumed a person who is indoors or fully shaded, unclothed, completely sedentary, not walking to the bathroom, not cooking food, not climbing stairs to check on a neighbor, fully acclimatized to heat, meaning weeks of prior exposure, and of average size, which in the modeling context meant a kind of idealized thermal mass that does not correspond to any specific real person. Those assumptions are not real life. They are not close to real life. And in 2022, a team at Penn State decided to find out what the actual number is. W. Larry Kenney, professor of physiology and kinesiology, Marie Underhill, Knoll Chair in Human Performance, one of the leading heat stress researchers in the country, led what they called the PSU Heat Project, Human Environmental Age Thresholds. The name itself tells you what they were after, not the theoretical limits of a thermodynamic model, but the actual physiological limits of real human beings at different ages. They put 24 young, healthy adults into a controlled environmental chamber, 11 men, 13 women, ages 18 to 34. They placed skin sensors at the chest, upper arm, inner thigh, and calf. They measured core temperature with gastrointestinal telemetry capsules, tiny sensors the subjects swallowed that transmitted real-time temperature data from inside the body. And then they raised the temperature and humidity in carefully controlled increments while the subjects performed light physical activity, walking slowly on a treadmill, pedaling a cycle ergometer at minimal intensity, simulating daily life, not exercise, not labor, just existing as a human being in a hot room. The results landed like a stone in a quiet room. No subject, not one, reached the theoretical 35-degree threshold before their body's cooling system failed. The actual critical wet bulb temperature, averaged across all subjects in humid conditions, was 30.55 degrees Celsius, plus or minus 98 hundredths. Call it 31. That is 87.8 degrees Fahrenheit, 4 degrees lower than the number on every planning document, every risk assessment, every IPCC projection. And I need you to understand what 4 degrees means in this context, because it is not what it sounds like. 4 degrees on a regular thermometer, the difference between 72 and 76 is negligible. You would not notice it. But 4 degrees on the wet bulb scale, at the boundary where human physiology fails, is the distance between a system that can protect you and a system that has already failed by the time someone realizes it should be working harder. It is the distance between discomfort and death, and the safety margin that every planner, every emergency manager, every IPCC author assumed existed between current conditions and the limit. Case. That margin was never as wide as anyone thought. Daniel Vecellio, lead author on the companion paper, put the finding in the language that matters for everything that follows. A wet bulb temperature threshold cannot be applied uniformly across all climatic conditions, and where it is appropriate, DARF, in high humidity, that threshold is well below 35 degrees. And these were young, healthy people, the fittest demographic, the people most able to tolerate heat, the people who die in heat waves. The elderly, the chronically ill, the isolated were not in the chamber. Part 3, the body's last defense. I need to explain what wet bulb temperature actually measures, because without understanding this, the rest of the investigation will not land the way it needs to. Your body is a furnace. That is not a metaphor. It is engineering. At rest, sitting in a chair, reading, breathing, you produce roughly 80 to 100 watts of heat, just by being alive. Walk across the room and you are 150 watts. Cook dinner, standing, stirring, Reaching for ingredients? 200. Mow the lawn, and you are pushing 400 watts of metabolic heat that has to leave your body or your core temperature will rise. And above roughly 40 degrees Celsius, 104 Fahrenheit, measured inside your body, your organs begin to take damage. Proteins denature, cell membranes lose integrity. The heart, which is already working harder to push blood toward the skin for cooling, begins to fail. The brain, which is exquisitely, no, let me say this plainly, incredibly sensitive to temperature, starts to shut down. This is heat stroke, and it kills faster than most people realize. Your primary cooling system, your only meaningful cooling system, geese, is sweat. Liquid water on the surface of your skin evaporates, and evaporation is an endothermic process. It pulls heat energy away from your body. This is remarkably effective. On a dry, hot day, a person can shed several hundred watts of heat through sweating alone. As long as the air surrounding you can absorb more moisture, your sweat evaporates, your skin cools, blood flowing near the surface carries that coolness back into your core, and your internal temperature stays in the safe range. But evaporation needs a gradient. It needs the air to be drier than the film of sweat on your skin. When the humidity climbs, when the air is already holding a high percentage of the water vapor it can carry, the evaporation rate slows. And when the air is fully saturated, when the atmosphere cannot accept any more moisture, your sweat does not evaporate at all. It sits on your skin, beads up, drips off your chin and soaks your shirt, and does nothing, provides zero cooling. Your body is still producing 80, 100, 200 watts of heat, and none of it is leaving. There is no plan B. Sweating is the last line of defense, and when humidity kills it, core temperature begins climbing on a curve that does not bend back down without intervention. Wet bulb temperature captures exactly this. Imagine wrapping a thermometer in a wet cloth and blowing air across it. The water in the cloth evaporates, cooling the thermometer, exactly the way sweat cools your skin. The temperature that thermometer settles at is the wet bulb temperature. When it matches your skin temperature, roughly 35 degrees Celsius, evaporation stops completely. The wet cloth cannot cool the thermometer any further, and your body cannot cool itself any further either. Except the Penn State data showed the system breaks down well before that theoretical wall. And in 2023, Jennifer Vanos at Arizona State and Ollie J at the University of Sydney pushed the analysis much further. They built a physiological model, not a thermodynamic one, a model grounded in actual human biology that accounted for variations in age, body composition, sun exposure, and activity level. Their paper, published in Nature Communications, recalculated survivability limits using biophysical principles instead of idealized thermal assumptions. For young adults, their updated survivability limits range from 25.8 to 34.1 degrees Celsius wet bulb, depending on conditions. For older adults, the range dropped to 21.9 to 33.7 degrees. That lower bound, 21.9 degrees Celsius, roughly 71 degrees Fahrenheit on the wet bulb scale, corresponds to conditions that occur regularly in the southeastern United States every summer. Not during a heat wave, during a normal July afternoon in Mobile or Lake Charles or Pensacola. The sentence from the paper that I keep coming back to is this: the commonly used 35-degree model shows a vast underestimation of risks. The updated survivability limits are 0.9 to 13.1 degrees Celsius lower than the canonical threshold. 13 degrees of error, in a field where a single degree determines whether someone lives or dies. And there is another dimension to this that the published papers handle carefully, but that I think deserves plain language. The Vanos and J model did not just find that the threshold is lower. It found that the threshold is variable. It depends on who you are. A young, fit person in the shade has a very different limit than a 78-year-old on blood pressure medication walking from the parking lot to the pharmacy. And the people most exposed to Gulf Coast heat, the outdoor workers, the elderly on fixed incomes in homes with aging AC, the construction crews, and farmhands and delivery drivers, are not the young, healthy subjects in the Penn State chamber. They are the population for whom the lower bounds of the Vanos model apply, bounds that correspond to conditions already routine on the Gulf Coast. OSHA's proposed heat standard, published in August 2024, the first federal attempt to regulate workplace heat exposure in the agency's history, uses an initial trigger of 80 degrees Fahrenheit heat index and a high heat trigger of 90 degrees. But the proposed rule does not reference the Penn State findings. It does not reference the Vanos physiology model. It uses the older framework. And the informal public hearing on that proposed rule concluded in July of 2025. As of this recording, the final rule has not been issued. The gap between the science and the regulation is not closing. It is sitting open. Part 4, where it is already happening. So the threshold is wrong. It is lower than we thought, significantly lower, and the peer-reviewed evidence supporting that conclusion is not ambiguous. But the question that follows is the one that keeps me awake. How often are we already exceeding the real threshold? Colin Raymond whilst then a PhD student at Columbia University, now a postdoctoral researcher at NASA's Jet Propulsion Laboratory, decided to find out. And the way he found out tells you something important about why this problem was invisible for so long. Previous studies had looked at wet bulb temperatures using gridded reanalysis data. Think of these as climate models that smooth observations across broad geographic areas. One data point for every area the size of Rhode Island. That kind of averaging is useful for tracking global trends, but it obscures the localized spikes, the places where humidity surges for an hour, 2 hours, at a single coastal weather station sitting 10 kilometers from the Gulf of Mexico, the places where the sea breeze carries a pulse of 88 degrees seawater vapor directly over a populated coast, and the wet bulb temperature jumps past the threshold for a brief, dangerous window. Raymond and his co-authors, Tom Matthews at Loughborough University in the United Kingdom, and Radley Horton at Columbia's Lamont Doherty Earth Observatory, went to the raw station data instead. Over 7,000 weather stations around the world, going back to 1979. Nearly 4 decades of hourly observations. And what they found, published in Science Advances in May of 2020, changed the timeline on everything. They identified over 7,000 past occurrences of wet bulb temperatures above 31 degrees Celsius, above the empirical limit that the Penn State study would later establish as the actual threshold for young, healthy adults. Over 250 readings above 33 degrees. And the finding that turned heads in every climate lab in the world, 2 stations had already recorded wet bulb temperatures above 35 degrees Celsius. The theoretical ceiling, the number that was not supposed to be reached until the middle of this century according to every climate model projection, had already been breached. Briefly, locally. But it had been breached, and the frequency data was just as alarming. The study found that local instances of extreme humid heat, defined as a wet bulb temperature of 27 degrees Celsius, 80.6 Fahrenheit, or above, doubled from 1979 to 2017. Scientists had previously believed that wet bulb temperatures rarely reached 31 degrees Celsius. Raymond's team found recordings of that temperature over 1,000 times in the station record. Readings of 33 degrees, thought to almost never occur, appeared nearly 80 times. The models had not just underestimated the future, they had failed to see the present. Previous studies projected that this would happen several decades from now. Raymond told Columbia's news office, but this shows it's happening right now. And what he found about the geographic signature of these extremes is critical for this investigation. The most dangerous readings clustered on coastlines along confined seas, gulfs, and straits, exactly the kind of geography the Gulf of Mexico provides. Warm, semi-enclosed bodies of water that feed moisture into the air above them. The southeastern United States saw extreme conditions dozens of times during the study period, mainly near the Gulf Coast. East Texas, Louisiana, Mississippi, Alabama, the Florida Panhandle. The worst spots, and Raymond was specific about this, were New Orleans and Biloxi. El Fadi El Tahir at MIT, who was not involved in Raymond's study, but has done foundational work on wet bulb projections for the Persian Gulf and South Asia, described the findings as important because it builds on station data, which is the most direct evidence that we usually have. The station data is not a model output, it is not a projection, it is a thermometer reading at a specific place at a specific time, and those readings are exceeding thresholds that the projection said would not be reached for decades. The spatial pattern was tight. The intensity of extreme humid heat, Raymond found, is confined very closely to the coastline. That's to 10 to 20 kilometers, 6 to 12 miles. That is not a buffer zone. That is a metro area. That is downtown Galveston. That is the population of coastal Mobile County. That is the suburbs of New Orleans spilling into St. Bernard and Jefferson Parish. These are not rural observation points. These are the backyards of millions of people. And Climate Central's analysis, released just days ago, quantified it for the most recent decade. Some areas of the Gulf Coast are now experiencing more than 100 dangerous humid heat days annually on average during 2016 to 2025, not 100 hot days. 100 days where the heat-humidity combination crosses into the range that the updated physiology says is biologically dangerous for vulnerable populations. Raymond described the trend as the most important takeaway. It didn't matter what level of extremeness we looked at or what part of the world, the trends were upward across the board. The trend is not leveling off. It is accelerating. Part 5, the night that does not cool. Here is something the daytime temperature forecast does not tell you. It does not tell you whether you will survive the night. In every major heat disaster in modern history, every single one, from Chicago to Paris to Karachi, the factor that tipped discomfort into mass casualty was not the peak afternoon temperature. It was the overnight low. When the sun goes down and the temperature does not follow it. When the air stays hot and saturated through the dark hours. When the walls of a building that absorbed heat all day begin radiating it inward, and the interior temperature of a home without air conditioning exceeds the exterior temperature even as the rest of the world technically cools. That is when people die, not at 3 in the afternoon when the heat index is on the news and people are paying attention and the warnings are scrolling across the bottom of the screen. At 3 in the morning when no one is watching, when the emergency has become invisible, because the sun went down and the assumption, the deep, unconscious assumption built into every emergency notification system, is that nighttime means relief. Picture a second-floor apartment in a brick building in the 9th Ward of New Orleans in late July. No air conditioning. The unit has a window unit, but the compressor failed last summer, and the landlord has not replaced it. The building faces west, which means the afternoon sun pounds directly into the brick for 6 hours before sunset. By 9 p.m., the exterior wall is a radiant heater. The interior temperature has climbed to 94 degrees. The occupant, say she is 73, lives alone, takes hydrochlorothiazide for blood pressure, opens the windows. The air that enters is 84 degrees, with a dew point of 79. Her sweat beads, but does not evaporate efficiently. She drinks water, lies down, turns on a box fan. The fan pushes saturated air across her skin, but the evaporative gradient is too small. By midnight, the apartment is 91 degrees. Her core temperature has risen half a degree. By 2 a.m., it has risen another half degree. She feels dizzy. She does not call anyone because she has been hot before. She has survived every summer in this apartment for 11 years. She assumes this is the same. It is not the same. The wet bulb temperature in her apartment, if you measured it, would read approximately 30 degrees Celsius, 1 degree below the Penn State threshold for young adults. She is not young. She is on a medication that impairs sweating. Her personal threshold, according to the Vanos and J model, is somewhere around 25 or 26 degrees. She crossed it hours ago. This is not a hypothetical. This is the demographic and geographic intersection that produces every heat death in the United States. And it happens in silence, at night, in rooms nobody is monitoring. On the Gulf Coast, nighttime does not mean relief. Coastal cities receive a continuous supply of moisture from the Gulf. The humidity does not dissipate after dark because the source of the moisture, 88 degrees seawater, measured at the surface and extending warm 100 meters below, is still there, still evaporating, still loading the air. Dew points along the Gulf Coast routinely stay above 75 degrees Fahrenheit overnight in July and August, sometimes above 80. And when the dew point is that high, even a modest overnight air temperature of 85 or 88 degrees produces a wet bulb reading that lands in the range the Penn State study identified as dangerous. And the Texas Observer reported this week, as in the week you are hearing this, that ERCOT's overnight recovery window is shrinking. The high demand season is starting earlier and lasting longer. In May 2025, ERCOT set a new spring demand record of 78,392 megawatts, a number that would have been an all-time summer peak just a few years earlier. The gap between what the Texas grid was planned to handle and what it is now being asked to support is widest when cooling demand no longer drops the way the engineering once counted on. And OSHA's first ever proposed federal heat standard, published for public comment in August of 2024, uses an initial trigger of 80 degrees Fahrenheit heat index. That is a daytime standard. There is no federal nighttime standard, no federal guidance that addresses what happens when the overnight low inside a home without functional air conditioning exceeds the threshold at which human physiology begins to fail. That gap in the regulatory framework is not an oversight anyone is rushing to close. But the overnight recovery failure is only half the story, because the grid is not just carrying the weight of residential air conditioning. It is carrying new load that did not exist 5 years ago. Data centers, cryptocurrency mining operations, industrial facilities, a baseline demand that runs at all hours, does not respond to temperature, and creates a permanent floor beneath the demand curve that compresses the margins the grid relies on during peaks. That demand is about to collide with a summer that every forecasting product in the country is pointing in the same direction. The question this investigation spends the next hour answering is not whether the heat is coming. It is. The question is what happens to the people in its path when the machine that protects them from the threshold, the grid, the AC, the cooling infrastructure, fails during the exact conditions when failure is lethal. And to answer that, I need to take you inside the grid itself, because what I found there is not reassuring. Part 6, the machine between you and the threshold. I want you to hold two numbers in your head at the same time. The first is 31 degrees Celsius, 87.8 Fahrenheit, the empirically determined wet bulb temperature at which a young, healthy human body can no longer cool itself. The second is the wattage your body produces just by being alive. At rest, you're an 80-watt space heater. Walk across the room, you're 150. Cook dinner, 200. Mow the lawn, and you're pushing 400 watts of metabolic heat that has to go somewhere. Air conditioning does not cool you, not directly. What it does is maintain an artificial microclimate, or a pocket of dry, cool air around your body that allows your sweat to keep evaporating. It keeps the gradient alive. It keeps the wet bulb temperature in your personal airspace below the threshold so that your biology can function as designed. This is why calling AC a comfort appliance in the Gulf Coast context is not just wrong, it is dangerous. In a region where overnight wet bulb temperatures routinely exceed 30 degrees and trend toward 31, air conditioning is a life support system. The moment it fails, the clock starts. And the clock is not abstract. It is metabolic. Your body does not stop producing heat when the AC fails. You are still generating 80, 100, 150 watts of thermal energy that has to go somewhere. And in a sealed apartment at 96 degrees, with a dew point of 79, it has nowhere to go. The first hour, your core temperature rises a few tenths of a degree. Your heart rate increases as blood flow shifts toward the skin in a futile attempt to dump heat to air that cannot absorb it. Your kidneys begin concentrating urine to preserve fluid. By the second hour, your core temperature has climbed past 38 degrees Celsius. By the fourth, you may be approaching 39. Confusion sets in. Decision-making degrades, which means you become less likely to call for help precisely as you need it most. For an elderly person on a diuretic, a medication that reduces blood volume, which impairs the cardiovascular system's ability to circulate blood to the skin, the timeline compresses. The physiological margin between uncomfortable and organ damage narrows to the point where a single missed welfare check can be the difference between intervention and death. And I know exactly what that compressed timeline looks like at the population level, because Chicago showed us. July 12, 1995. Midway Airport recorded a high of 106 degrees Fahrenheit. The dew point, a direct measure of how much moisture the air is carrying, sat at 80 degrees. Tom Skilling, one of the most respected meteorologists in the country, had predicted the heat. Even he did not foresee the horror. "We saw heat coming," he said during the 30th anniversary retrospective. It was so extreme that it even exceeded what our computer models were forecasting. But we corrected for the heat and accurately predicted the high. That's an incredible amount of moisture in the air. The heat index, the number that tries to capture what the combination of temperature and humidity actually feels like against human skin, hit 125 degrees. A Los Angeles Times reporter on the street at midday observed that Chicagoans seemed to be walking in a daze. But Chicago was not a city built to daze its residents with heat. It was a cold weather city, a wind chill city. The infrastructure, the housing stock, the emergency protocols, the public health apparatus had been calibrated for blizzards and ice storms. Air conditioning was not universal. In the poorest neighborhoods on the south and west sides, Inglewood, Fuller Park, Roseland, North Lawndale, many residents had never installed it. Some had units that no longer worked. Some had units they could not afford to run. Some had units but feared that opening windows, the alternative when AC failed, would invite the violence that plagued their blocks in the summer of 1995. But here is what made Chicago a killing event, and not just a miserable week. The nighttime low temperatures never dropped below 80, 5 consecutive nights. The city never exhaled. The brick and concrete and asphalt of Chicago's south and west sides, Inglewood, Fuller Park, Roseland, had been absorbing thermal energy for 72 hours. And on the second and third nights, the buildings began returning that energy into the apartments of the people inside them. The grid buckled. 49,000 homes lost power as transformers overheated and failed under the demand. And here is the finding from the forensic reconstruction that I think is the most important data point in this section. The peak indoor temperatures in homes where people died did not coincide with the peak outdoor temperatures. They lagged by 2 days. The deadliest conditions inside those apartments arrived after the worst of the heat had technically begun to break outdoors. The buildings had become thermal batteries, and they were discharging into sealed rooms where elderly residents, many of them alone, many of them afraid to open windows because of crime, many of them without functioning air conditioning or unable to afford to run it, sat in the dark. 739 people died in 5 days, more than twice the death toll of the Great Chicago Fire. 72% of the victims were over 65. Black residents died at 1.5 times the rate of white residents. Eric Kleinenberg, the sociologist who wrote the definitive analysis, Doc Heat Wave, A Social Autopsy of Disaster in Chicago, showed that the deaths were not randomly distributed. They clustered in neighborhoods with the highest rates of elderly isolation, the oldest housing stock, the least social cohesion, and the poorest access to cooling. The Cook County Medical Examiner's Office ran out of space. Bodies were stored in refrigerated trucks because the morgue could not hold them. And when families did not come forward to claim the dead, because in many cases no one knew the person had died, because the person lived alone, because the social connections that might have produced a welfare check had already frayed, the unclaimed were buried in mass graves. Eric Kleinberg, the sociologist who wrote the definitive analysis, Heat Wave, A Social Autopsy of Disaster in Chicago, showed that the deaths were not randomly distributed. They clustered in neighborhoods with the highest rates of elderly isolation, the oldest housing stock, the least social cohesion, and the poorest access to cooling. But Kleinenberg's most important finding, the one that connects Chicago to the Gulf Coast scenario, was about the nature of the failure itself. It was not a natural disaster in the way people usually use that term. It was an infrastructure disaster, a governance disaster, a disaster of assumption. The city's emergency management system had been built around the threats it could see and name. Tornadoes? Blizzards? Chemical spills? Nobody had gamed out a heat wave. Nobody had assigned it a threat level. Nobody had pre-positioned resources for an event where the emergency was invisible, where the dying happened silently, indoors, behind closed doors, in rooms where no alarm went off and no flood wall was breached. The heat killed precisely the people the system could not see. That was Chicago, in the Midwest, in 1995, a city with lower baseline humidity than any Gulf Coast metro, a city where wet bulb temperatures during the event never approached the thresholds the Penn State study would later identify as the boundary of physiological failure. Now put that event on the Gulf Coast, with warmer baseline temperatures, with higher baseline humidity, with wet bulb readings that the station data says are already routinely exceeding the updated thresholds for vulnerable populations, and with a power grid that just received a D+ from the American Society of Civil Engineers, an assessment published in the 2025 Infrastructure Report Card that flagged capacity, future needs, and safety as critical weaknesses requiring hundreds of billions in additional investment. Part 7, the grid that carries the weight. ERCOT, the Electric Reliability Council of Texas, operates the power grid for 90% of the state's electrical load. And ERCOT's grid is not like other grids. By design, it has only 4 relatively small transmission connections to neighboring systems. It was built to operate as an island. The advantage was regulatory independence. The disadvantage is that when demand spikes and generators fail, ERCOT cannot import significant power from outside Texas the way grid operators in the eastern or western interconnections can. This is the grid that failed during Winter Storm Uri in 2021, leaving millions without power or heat. And I need to be specific about what failed means, because the word does not capture the scale. During Uri, the ERCOT system came within 4 minutes and 37 seconds of a cascading grid collapse, a complete, uncontrolled shutdown that would have physically damaged generators across the state and taken not days but weeks to restore. 4 minutes, the margin was 4 minutes, between a multi-day blackout and a multi-week catastrophe affecting 26 million people. In sub-freezing temperatures, over 200 people died. And the failure mode that Uri exposed is structurally relevant to the heat scenario. ERCOT's island design means it cannot lean on its neighbors. During Uri, the 4 small DC ties connecting ERCOT to the eastern and western interconnections provided a trickle, roughly 1,000 megawatts, while the system needed tens of thousands. The same limitation applies in a summer emergency. When a heat dome is parked over Texas and demand spikes past 90 gigawatts, ERCOT cannot pick up the phone and import 10 gigawatts from Oklahoma or Louisiana, the way PJM or MISO can share capacity within the Eastern interconnection. The Texas grid succeeds or fails on its own generation. That is the design. And that design is now being asked to carry a load it was never engineered to handle. Here are the numbers, and I want you to track the acceleration because it tells you something the summary statistics cannot. In 2022, ERCOT's peak hourly demand was 79,830 megawatt hours, a record at the time. In 2023, the second hottest Texas summer on record, peak demand reached 85,508 megawatts, a new all-time record. The grid held, but barely. ERCOT entered an emergency operating condition in September 2023 when reserves dropped during a late-season heat wave, the kind of event that used to be confined to July and August. In 2024, the record broke again, 85,559 megawatts, set on August 20th. ERCOT navigated that peak without conservation requests, a genuine operational improvement driven largely by the addition of solar and battery storage capacity. That progress is real and should not be dismissed. But the number that should unsettle you is not either of those summer peaks. In May of 2025, May, not July, not August, ERCOT set a new spring demand record of 78,392 megawatts. That is summer-level demand showing up in spring. To put that in context, the all-time peak demand record from 2022 hours set during the hottest week of the year, was only 1,500 megawatts higher than what May of 2025 produced during a heat event that would have been unremarkable in August a decade ago. The high demand season is migrating earlier in the calendar, and the grid's planning models were not built for that migration. And now, this week, as in the week you are hearing this, ERCOT released its summer 2026 forecast. Dan Woodfin, ERCOT's Vice President of System Operations, told the board that demand could reach just over 92 gigawatts. That would shatter the existing record by more than 6 gigawatts. A single gigawatt powers roughly 200,000 Texas homes on a hot summer day. 6 gigawatts is 1.2 million homes worth of additional demand that the system has never been asked to deliver. And the question of where that demand is coming from has an answer that splits into two channels, both of which are accelerating. The first channel is heat. NOAA's summer outlook favors above normal temperatures, and El Niño is building toward a potentially strong event. Every degree of additional ambient temperature drives residential cooling demand higher, not linearly, but on an exponential curve, because as temperatures climb, air conditioning systems run longer cycles, draw more current, and push the grid harder per household. The second channel is structural, and it is the one that keeps grid analysts awake. Since September, approximately half a gigawatt of cryptocurrency mining has connected to the ERCOT grid. And the interconnection queue, the pipeline of large load projects waiting to plug in, has swollen to over 230 gigawatts of requests, nearly 4 times the level from the prior year. Data centers, crypto, industrial load. These facilities draw power continuously. They do not cycle off at night. They do not respond to temperature. They create a permanent floor beneath the demand curve that compresses the margins the grid relies on during peaks. The Energy Information Administration projects ERCOT electricity demand will rise by roughly 14% in 2026 as these large loads come fully online. And the ASCE's 2025 infrastructure report card downgraded the nation's energy sector, which includes electrical transmission, from a C- to a D+. The reason? Concerns related to capacity, future needs, and safety. Hundreds of billions in additional investment required. And there is a timing vulnerability in ERCOT's architecture that maps directly onto the compound threat this investigation is tracking. On hot summer days, ERCOT's highest risk period is not the afternoon peak, when solar generation is at its highest and is helping carry the load. The highest risk window falls between 8 and 9 p.m., when the sun drops below the angle at which solar panels produce useful output. But the air temperature has barely fallen, and every air conditioning unit in the state is still running full blast. This is the gap. Solar output drops by thousands of megawatts over the course of an hour. Natural gas plants and battery storage have to ramp up to fill the hole. And if a major generating unit trips offline during that transition, if a natural gas plant has a forced outage, if a transmission line sags and faults in the heat, the reserves can evaporate in minutes. ERCOT's grid operators know this. They manage it every summer, but they have never managed it at 92 gigawatts. And they have never managed it during a summer when the El Niño signal and the Gulf SST anomaly are both pointing in the same direction. So let me draw the picture plainly. The Gulf Coast's wet bulb temperatures are trending toward and occasionally exceeding the empirically determined threshold at which human cooling fails. The only system standing between tens of millions of people and that threshold is an air conditioning fleet powered by a grid that just received a near failing grade, is carrying unprecedented demand, and is about to be asked to do something it has never done. In the hottest months, under the highest humidity, with no significant ability to borrow power from anyone else. And this is where the two stories, the wet bulb threshold and the power grid, converge on the same geography at the same time in a way that no one is adequately modeling. Part 8, the Gulf's fingerprint. I need to pull back from the grid for a moment and take you underneath the surface of the Gulf of Mexico, because what is happening in that water is the driver that connects the heat, the humidity, and the hurricane risk into a single compound threat. Brian McNulty at the University of Miami has been tracking ocean heat content in the Gulf since 2013. His graphs, which are public, which you can pull up yourself at his research page, show something that looks less like a gradual warming trend and more like a staircase. Each year ratchets higher. Each summer starts from a higher baseline than the one before. And the staircase metaphor is more precise than it might seem because it is not just the surface warming. The heat is penetrating deeper into the water column with each successive cycle, building a reservoir of thermal energy that persists through the winter and provides a running head start for the following summer. The mechanism driving this is the loop current, a wide ribbon of water that enters the Gulf through the Yucatan Channel between Cuba and Mexico, curves northward into the basin, and exits past the southern tip of Florida to become the Gulf Stream. It moves at roughly 1.8 miles per hour. That is fast for an ocean current, and it carries Caribbean warmth deep into the Gulf Basin. Think of it as a conveyor belt delivering thermal energy from the tropics and depositing it on the shallow continental shelf off the Texas, Louisiana, Mississippi, and Alabama coasts. When the loop current extends far into the Gulf, what oceanographers call a port or extended position, it floods the northern shelf with warm water. Not just at the surface, down to 100 meters and below. And that deep warmth is the critical variable because it means the thermal energy is not a thin surface film that a cold front or a storm can easily scrub away. It is structural, embedded in the water column, persistent. A research team studying Hurricane Michael in 2018 found that a marine heat wave on the northern Gulf Shelf, triggered by a sequence of compounding atmospheric events, contributed to the extreme ocean heat content that fueled Michael's rapid intensification before landfall. The same compound mechanism is at play every hurricane season. Atmospheric events heat the shelf. The shelf retains the heat, and the retained heat becomes fuel for the next storm. This matters for two reasons, and they feed the same threat. The first is moisture loading. Warm water evaporates. The warmer the water, the more aggressively it feeds moisture into the overlying atmosphere. This relationship follows the Clausius-Clapeyron equation, but you do not need to know the name to understand what it does. For every degree Celsius the ocean surface warms, the atmosphere above it can hold roughly 7% more water vapor. That is not linear, it is exponential. And when a heat dome parks over the Gulf, and the spring 2026 forecasts already identified this as a likely pattern, the dome traps that moisture-laden air over the coastal states. It cannot escape vertically because the high pressure is capping it. It cannot escape laterally because the dome is too broad. So the moisture accumulates. Day after day, dew points climb, and wet bulb temperatures begin their approach toward the threshold. This is why the Gulf Coast wet bulb problem is structurally different from the dry heat problem in Phoenix or Las Vegas. In the desert Southwest, the air temperature can reach 120 degrees, but the wet bulb temperature stays manageable because the humidity is low, often in single digits. Sweat evaporates instantly. The body's cooling system works. On the Gulf Coast, the air temperature might only be 95 or 98 degrees, numbers that do not make the national news, but the dew point is running at 78 or 80, and the wet bulb temperature is approaching or exceeding the threshold where biology breaks down. The danger is invisible in the standard temperature forecast. You have to know to look at the moisture. The second reason the Gulf warming matters is more alarming and connects directly to the compound event I am building toward. That same deep warm water, the energy stored in the Gulf's water column, is the fuel supply for hurricanes. When a tropical system passes over shallow warm water, its winds churn up cooler water from the depths, which puts the brakes on intensification. But when the warm water extends 100 meters down, there's no cold water to churn up. The hurricane's winds just stir up more warm fuel, and the storm intensifies, sometimes explosively. This is what happened with Hurricane Helene in 2024. The Gulf's thermal reservoir allowed furious intensification as the storm bore down on Florida's Big Bend, and Kim Wood's seasonal forecasts, using NOAA's CFS model, suggest the Gulf will remain anomalously warm through the peak of the 2026 hurricane season. So the Gulf is doing two things simultaneously to the same geography. It is loading the atmosphere with the moisture that drives wet bulb temperatures toward the threshold, and it is fueling the hurricanes that destroy the power grid. The grid that is the only thing standing between the population and the threshold. That is not a coincidence of risks. It is a coupled system, one hand pushing two levers. Part 9, the Hurricane Multiplier. On July 8, 2024, Hurricane Beryl made landfall near Matagorda, Texas, as a Category 1 storm. The wind damage was significant, but survivable. The storm surge was manageable. What killed people was what came after. Beryl knocked out power to roughly 2.7 million customers across the Houston metro area, and then the heat dome that had been building over the southern plains settled directly over the region. Temperatures climbed past 100 degrees. Humidity was oppressive. The wet bulb temperature in parts of Harris County, if you calculated it from the observed temperature and dew point, which the standard NWS products do not report directly, sat above 29 degrees Celsius for extended periods. That is 2 degrees below the Penn State threshold for young, healthy adults. For elderly residents on the second floor of a blacked-out apartment complex in the 3rd Ward, the personal threshold had already been crossed. 14 people died of heat-related causes in the days following the storm. 14 people died not because of the hurricane, not because of the wind or the surge or the flooding. They died because the hurricane removed the machine that was keeping them alive in the heat. And I need you to sit with that distinction because it changes how you assess the risk. The threat model that emergency management is built around, the hurricane is the disaster, and the heat is the recovery environment, has it backwards in the Gulf Coast summer. The heat is the disaster. The hurricane is the trigger that removes the protection. And this is not an isolated case. The pattern is now documented well enough to name. Since 2017, there have been 4 United States hurricane landfalls, where multiple heat-related deaths occurred during a heat wave that followed massive post-storm power outages. Beryl in 2024, Hurricane Irma in 2017, 14 dead in South Florida, including 12 residents at a single nursing home in Hollywood, Florida, where the air conditioning failed and the backup generator could not power the cooling system. Hurricane Laura in 2020, and Hurricane Ida in 2021, which caused the largest power outage in Louisiana history, over 1 million customers, more than 2 million people, in the dark, in the last week of August, in the Gulf Coast summer. The Ida aftermath deserves particular attention because it is the closest precedent to the full compound scenario. Ida made landfall on August 29th, exactly 16 years to the day after Hurricane Katrina, as a Category 4 storm near Port Fourchon, Louisiana. The Entergy Louisiana grid was devastated. All 8 transmission lines serving the New Orleans metro area went down. The city, its hospitals, its water treatment plants, its cooling infrastructure lost power completely. And it lost power during the hottest, most humid week of the summer. In the days that followed, the NWS office in Slidell issued heat advisories for the New Orleans metro area. Heat index values reached 108, 110, 112 degrees, and these advisories were being issued for a population with no air conditioning, no reliable refrigeration, limited potable water, and roads too debris-choked for supply trucks or ambulances to navigate effectively. Some neighborhoods did not have power restored for 3 weeks. 3 weeks without cooling, in September on the Gulf Coast. The official heat death toll from Ida was relatively small compared to the storm's direct fatalities, partly because a massive evacuation had reduced the population in the hardest hit areas, and partly because heat deaths are systematically undercounted on death certificates. But the mechanism? Hurricane removes grid, heat dome settles over blacked out region, vulnerable population trapped indoors without cooling, was fully operational. The event was a dress rehearsal, and the lesson it taught is the lesson that every compound event in this investigation reinforces. The same ocean that fuels the storm fuels the heat that follows it. The nighttime satellite imagery of New Orleans before and after Ida, captured by the Suomi NPP satellite, is as stark as any image I have ever encountered in this work. Before, a city lit up, the grid functioning, the infrastructure holding, the outline of Lake Pontchartrain visible from the glow of the metro area surrounding it. After, darkness, near total darkness. The lights of the city replaced by scattered pinpoints of diesel generators, backup power that the utilities do not monitor, that is not connected to any coordinated emergency response, that runs until the fuel runs out and then stops. And the fuel trucks cannot get through because the roads are blocked by storm debris. Ida knocked out power to over 1 million customers in Louisiana in the last week of August. Peak humidity season, peak heat season. The New Orleans area experienced temperatures in the mid-90s with dew points in the upper 70s for days after the storm. Wet bulb temperatures, calculated from the observed conditions, were well above 29 degrees Celsius, dangerously close to the Penn State threshold for young adults, and already past the Vanos J limits for elderly residents. Recovery took weeks in some neighborhoods, weeks without air conditioning. In August, on the Gulf Coast. Michael Oppenheimer at Princeton has been studying compound climate risk for 2 decades, and his framework for understanding these events is the one I keep returning to. In a 2025 interview, he stated what the data has been showing with increasing clarity. These are not just individual risks, they are combined risks. Consequences can be more severe than the sum of damages expected from the individual events, because they interact with each other. The damages from the first worsening the effect of the second event. That interaction, the damages from the first worsening the effect of the second, is the exact mechanism at work in every post-hurricane heat death. The hurricane is not separate from the heat wave. It is the event that converts the heat wave from a stress on the system into a mass casualty threat by removing the one layer of protection the population depends on. And a 2025 paper, projected increases in tropical cyclone-induced U.S. electric power outage risk. Use the latest generation of IPCC models to project what comes next. The finding, the risk of extended power outages from landfalling hurricanes is rising, driven by both stronger storms and more vulnerable infrastructure. The trend is not theoretical, it is a projection grounded in observed storm intensification rates and documented grid fragility. So here's the scenario that no emergency management plan I have seen adequately addresses. A major hurricane tracks across the Gulf of Mexico in August, across water running 6 to 7 degrees above the long-term average. The warm water allows rapid intensification. The storm makes landfall along the Gulf Coast, somewhere between Corpus Christi and Mobile. It knocks out power to millions of customers. 2 million, 3 million. The numbers from Beryl and Ida suggest this is the range. Roads are impassable for days. Cell towers are down. Emergency services are triaging storm damage. And then the heat dome that is already forecast to be present this summer reasserts itself over the region. Within 12 to 24 hours, wet bulb temperatures in the blacked out zone approach or exceed 31 degrees Celsius. The homes without power begin their 2-day thermal charging cycle. The same mechanism that the Chicago forensic reconstruction identified. Brick and concrete absorb heat all day and radiate it inward all night. Interior temperatures climb past 95, past 100, past 104. The people most vulnerable, the elderly, the isolated, those on medications that impair thermoregulation, those in mobile homes or second-floor apartments with metal roofing, are the last to be reached by emergency services that are already overwhelmed by storm damage. The ambulances are responding to downed power lines and flooded intersections. The cooling centers, if they exist, have no power either. The hospitals are running on generators with finite diesel supplies. And every hour that passes without restoration is an hour during which the wet bulb clock is ticking in every unventilated room in the outage zone. The research out of Chicago showed that the fatality risk in a heat wave triples without air conditioning. On the Gulf Coast, in a post-hurricane environment, with wet bulb temperatures the planning documents were never calibrated to handle, the multiplier could be significantly higher. The compound event does not add risks together. It multiplies them, and the multiplication happens in the gap between what the emergency plan assumes and what the atmosphere delivers. And what I have not yet told you is what the international data shows. What happens when this compound event occurs in a region with less infrastructure resilience than the United States? Because it has already happened, and the death tolls are not in the hundreds, they are in the thousands. Part 10, the people in the path. I have been talking about thresholds and grids and ocean temperatures, and all of that matters. The mechanism is real. The physics is sound. The data is not ambiguous. But mechanisms do not die. People die. And the specificity matters here. Who is in the path of this compound threat? Because the vulnerability is not evenly distributed, it never is. The arc from Brownsville, Texas to Pensacola, Florida, the coastline that Raymond's data identified as the epicenter of extreme humid heat in the United States, is home to roughly 35 million people. But that number, like the 35-degree threshold, hides more than it reveals. The population along the Gulf Coast is older than the national average in many of the most exposed counties. It is poorer. The housing stock is older. And the relationship between the population and the infrastructure protecting it is fractured along lines of income, age, race, and geography that determine with terrible precision who survives a compound heat event and who does not. In Harris County, Texas, the county containing Houston, population nearly $5 million, roughly 1 in 6 residents lives below the federal poverty line. In Orleans Parish, it is closer to 1 in 4. These are the residents most likely to live in older housing with inadequate insulation, aging AC units, and ductwork that leaks conditioned air into attic spaces. Air conditioning penetration, while high in aggregate, masks a reality that aggregate conceals. Having AC and having functional, reliable cooling that will protect you during a multi-day extreme heat event are not the same thing. A window unit from 2008 running at 60% capacity in a poorly sealed apartment on the second floor of a brick building is not going to hold interior temperatures below the wet bulb threshold during a 5-day heat dome. It is going to fail, quietly, without warning, in the middle of the night. A 2025 study published in Humanities and Social Sciences Communications built county-level Bayesian models of power outage duration across the Gulf Coast, combining outage data, disaster records, and social vulnerability information from 2017 through 2022. The finding that matters for this investigation: hurricanes and tropical storms were associated with the longest outage durations regionally, and the counties that recovered slowest were the ones with the highest social vulnerability scores. Not the counties with the worst infrastructure. The counties where the people were most isolated, most elderly, most without resources to self-evacuate or self-rescue. Think about what that means in the context of the compound event. The storm hits, the power goes out, recovery begins, but it begins according to a priority structure that was designed for a different threat model. Commercial corridors come back first. The economic engine, the supply chains, the hospitals. Wealthy neighborhoods with underground power lines and newer infrastructure come back second. The last blocks to get power restored are the blocks with the oldest above-ground distribution lines, the densest tree canopy dropping debris on wires, and the lowest political visibility. And those last restored blocks are not random. They are predictable. They are the same blocks every time. The neighborhoods where the housing stock is 60, 70, 80 years old, where the residents are on fixed incomes, where the average age is 10 to 15 years above the county median, where a single person living alone on the second floor of a brick apartment building may not have spoken to another human being in 4 days. The NWS Heat Risk Tool, expanded nationally in 2024, was designed in part to address this gap, to give emergency managers a forecast product specifically calibrated to heat health impacts rather than just raw temperature. But heat risk integration with county emergency operations varies widely. In some jurisdictions, a multi-day purple heat risk forecast triggers automatic activation of cooling centers, pre-positioned EMS resources, and welfare check protocols for registered vulnerable residents. In most Gulf Coast counties, it does not. The tool exists. The institutional infrastructure to act on it systematically does not. At least not yet, and not at the scale the exposure demands. And those are the blocks where the wet bulb clock is ticking hardest. I keep coming back to one specific case because it crystallizes everything about this gap. September 13, 2017. 3 days after Hurricane Irma passed through South Florida, the Rehabilitation Center at Hollywood Hills, a nursing home on the edge of the Hollywood-Fort Lauderdale metro area, had lost its main air conditioning system when the storm knocked out the building's transformer. The facility had a backup generator. It was operational, but it could not power the full HVAC system. It could run the lights, the medical equipment, the kitchen appliances. It could not run the cooling. For 3 days, staff called Florida Power and Light. They called the city of Hollywood. They left messages asking for priority restoration. The temperatures inside the facility climbed past 90, past 95. Residents, many of them in their 80s and 90s, many of them unable to move independently, many of them on medications that impair the body's ability to sweat, were fanning themselves with paper plates. Staff brought in portable spot coolers. They were insufficient against the thermal mass of the building. On the morning of September 13th, first responders were called to the building. They found residents in acute distress. 12 people died. Interior temperatures were later estimated to have exceeded 104 degrees. 12 people. In a licensed, staffed operational care facility in the United States, in a building that had power, just not enough power to run the cooling system. The broader post-Irma heat death toll reached 14 across the region, and the investigation that followed revealed something that connects directly to the planning gap this investigation is about. The facility had a hurricane preparedness plan, detailed, compliant with state requirements. It did not have a heat preparedness plan. The assumption embedded in the planning, the assumption nobody questioned, was that the threat was the storm. Wind, water, surge. The heat was classified as the recovery environment, not the primary hazard. But in the Gulf Coast, summer, the heat is not secondary. It is the baseline. It is the constant. And when the storm removes the infrastructure that holds the heat at bay, the baseline becomes the killer. Part 11, the world that is already there. If you want to know what a mass casualty wet bulb event looks like, if you want to see what happens when the threshold meets a population without reliable cooling infrastructure, you do not need to project forward. You need to look at the Indus Valley, at Karachi, at the coastal plains of the Persian Gulf, because these regions are not modeled scenarios. They are field data, and the field data is devastating. Raymond's study identified the Persian Gulf coastline as a global hotspot for extreme humid heat. Every station with adequate data reported wet bulb readings of 31 degrees Celsius or higher at least once every 3 years during the study period. The mechanism is the same one operating in the Gulf of Mexico. Warm sea surface temperatures, shallow coastal waters, and onshore winds that carry saturated air directly into populated areas. The worst readings were confined to 10 to 20 kilometers of the coastline. Dubai recorded its highest temperature on record twice in 2 consecutive days in May of 2025, 51.6 degrees Celsius, 124.9 Fahrenheit, breaking the previous record by a margin that startled the meteorological community. And the heat struck before the region's standard midday work bans had taken effect. The gap between where dangerous heat is arriving and where formal protections begin is widening every season. Jacobabad, Pakistan. Population roughly 191,000. A city in Sindh province, sitting in the Indus River Valley about 500 kilometers, 300 miles 80 inland from the coast. Colin Raymond's station data shows that Jacobabad has already recorded 6 days when the wet bulb temperature exceeded 35 degrees Celsius. The theoretical ceiling, the number that was supposed to be unreachable until mid-century. It has been reached 6 times at one city, and the mechanism that drives it there is directly relevant to the Gulf Coast. Extremely hot, humid air surging inland from warm ocean waters, combined with moisture from widespread agricultural irrigation that saturates the lower atmosphere even far from the coast. A 2021 Amnesty International report categorized Jacobabad as unlivable for humans. not because of conflict or poverty alone, although both are present, but because of the thermal environment. Colonel Ahmed Sumro, the district head of the nonprofit Public Primary Healthcare Institute and a resident of Jacobabad, described the annual reality. Every summer, many people, especially the poor, fall sick and die from the heat. In June 2015, a heat wave struck Sindh province. Temperatures in Karachi peaked at 44.8 degrees Celsius, 112.6 Fahrenheit. A low-pressure system associated with the monsoon stationed over the northern Arabian Sea blocked the coastal sea breeze, the cooling mechanism that Karachi's 15 million residents depended on. The afternoon onshore wind that pulls cooler, drier air from the Arabian Sea across the city vanished. The air stagnated, and in 3 days, approximately 2,000 people died. The toll accumulated with horrifying speed. On Sunday, the first day of the crisis, 136 people died. On Monday, 309. On Tuesday, 311 in Karachi alone, with additional deaths reported in Hyderabad, Badin, and Thata. The city's hospital system collapsed under the volume. Dr. Seeman Jamali, the Joint Executive Director of the Jinnah Postgraduate Medical Center, described it without euphemism. We are continuously receiving people in a critical condition or dead. There has been no let-up. The morgue at Jinnah alone recorded 279 deaths. Prolonged power cuts across the province, rolling blackouts that had been a chronic problem before the heat wave, knocked out air conditioning and fans for millions of people who had no alternative cooling source, no vehicle to drive to a cooler location, no second home to retreat to. 2,000 dead in 3 days in a single province of a single country. A 2015 EMDAT ranking placed the combined India-Pakistan heat wave of that year as the fourth deadliest heat wave in recorded human history, with 3,477 total deaths across both countries. The pattern is structurally identical to the compound event this investigation describes for the Gulf Coast. The atmospheric pattern blocks ventilation. The power fails. The cooling systems go offline, and the wet bulb temperature crosses the threshold. The real threshold, the one Penn State measured, not the one on the planning documents, in homes and buildings and care facilities where people cannot leave. And Karachi is not the worst-case historical precedent. Europe, August 2003. A heat dome settled over the continent for 2 weeks. It was hot and dry rather than hot and humid. A critical distinction because dry heat kills through a different mechanism, primarily dehydration and cardiovascular stress. But the structural lesson is the same. 72,000 people died across 16 European countries. The death toll dwarfs any hurricane, any earthquake, any single natural disaster in modern European history. In France alone, the peak was staggering. On August 4th, 300 excess deaths were recorded, an anomaly, but not yet an emergency in the official response. The numbers climbed through the following week. Public health officials who noticed the spike in emergency room visits struggled to escalate the warning because the bureaucratic chain of command was operating on summer schedules. By August 12th, excess deaths had climbed to 2,000 per day. 2,000 people per day dying of heat exposure in one of the wealthiest nations on earth. Bodies were stored in a refrigerated warehouse at the Rungus Wholesale Market, the massive food distribution center outside Paris, normally used to keep produce fresh because the city's morgues had been overwhelmed days earlier. The catastrophe occurred in August, when many government officials were on vacation. The recognition of the scale was slower than the dying. The institutional failure was not a failure of knowledge. French meteorologists had issued warnings. Medical researchers understood the relationship between heat and mortality. The failure was a failure of priority, of classification. Heat was not categorized alongside the threats that trigger automatic emergency response. It sat in a different mental category. Weather, discomfort, inconvenience. Not hazard, not crisis, not mass casualty event. The French heat wave investigation afterward reached a conclusion that should be printed on every emergency plan in every Gulf Coast county. While contingency plans were made for a variety of natural and man-made catastrophes, high temperatures had rarely been considered a major hazard. That sentence was written about France in 2003. It could be written about the American Gulf Coast today. And the difference, the variable that makes the Gulf Coast scenario potentially worse, is humidity. Europe's 2003 event was a dry heat event. The body could still sweat. It could still attempt to cool itself. The deaths were concentrated among the elderly, the isolated, those without access to water or shade or help. In a humid heat event, the kind the Gulf Coast is primed for, sweating itself fails. The thermodynamic wall arrives sooner at lower air temperatures, and it arrives for everyone, not just the vulnerable. The planning documents have not caught up to that distinction. Part 12, the claims that deserve real answers. Whenever I cover a topic like this, there are responses that circulate, some in good faith, some not, and the substantive ones deserve actual engagement with the physics, not dismissal. The first claim I see repeatedly is this: humans have always lived in hot climates. We adapt. This is fear-mongering. The impulse behind this claim is understandable. Humans have, in fact, colonized every latitude on this planet. We have built cities in deserts and on tropical floodplains and in river valleys that routinely hit 45 degrees Celsius in the shade. The adaptation is real, and it is remarkable. Acclimatization, the physiological process by which the body improves its sweating efficiency, expands its plasma volume, lowers its resting core temperature, is documented and significant. Epidemiological data shows a clear latitudinal dependence on the temperature at which mortality begins rising. Populations in hotter climates tolerate higher temperatures before health outcomes deteriorate. All of that is true, and none of it is relevant past the wet bulb threshold. Acclimatization improves the efficiency of evaporative cooling. It does not change the physics of evaporation. When the air is saturated, when the wet bulb temperature equals or exceeds skin temperature, it does not matter how efficient your sweat glands are. The moisture has nowhere to go. The gradient is gone. Acclimatization can push your critical limit a degree or two higher within the normal range. It cannot push you past the thermodynamic wall. The Penn State researchers specifically noted that their test subjects were not acclimatized, and they acknowledged this as a limitation. But subsequent modeling, including the Vanos and J 2023 paper, incorporated acclimatization into the physiology-based model and still found survivability limits dramatically below 35 degrees for real human populations. The wall is the wall. You can train for it. You cannot eliminate it. The second claim is more sophisticated and comes from a more interesting place. Air conditioning solves this. It is a technology problem, not a climate problem. Invest in the grid, expand AC access, and the wet bulb threshold is irrelevant. This is the honest Steelman, and it deserves full engagement because there is a genuine peer-reviewed substrate here. The history of human heat adaptation in the 20th century is, in significant part, a history of air conditioning deployment. Willis Carrier's invention in 1902 did not just change comfort, it changed demography. The population boom in the American Sunbelt after World War II is inseparable from the availability of affordable residential cooling. In that sense, the claim is correct. AC has been the single most consequential human adaptation to heat in modern history. Consider the numbers. In 1960, fewer than 15% of American homes had air conditioning. By 2020, the figure exceeded 90% nationally. In Texas, it approaches 98%. That deployment curve correlates directly with the flattening of heat mortality in the developed world during the second half of the 20th century. Even as temperatures climbed, heat deaths per capita declined in regions where AC penetration expanded. The technology did not eliminate the physiological threat. It eliminated the exposure. It put a machine between the population and the threshold. The claim that technology solves climate is doing real work here. It is not hand-waving. It is pointing at a 90-year track record of a specific technology dramatically reducing heat mortality in every country where it was deployed at scale. But the claim fails on three specific grounds, and precision matters on each one. First, the grid. The system that delivers the electricity to power the air conditioning just received a D+ from the most comprehensive infrastructure assessment in the country. That is not my characterization. That is the American Society of Civil Engineers 2025 report card. A system rated D+ is one with significant deficiencies and a strong risk of failure under stress. And the stress it faces: 92 gigawatts of projected peak demand, structural load growth from data centers and crypto mining, demand seasons that are starting earlier and lasting longer, is unprecedented. Second, compound events. AC solves the heat problem if and only if the AC is running. When the event that removes AC is the same event that creates the most dangerous heat conditions. A hurricane knocking out the Gulf Coast grid in August distilled the technology solution and the climate problem collapse into the same failure mode. You cannot air condition your way out of a blackout. Third, coverage. 100% AC penetration does not exist. Not in the United States. Not anywhere. In the counties along the Gulf Coast, with the highest social vulnerability scores, the ones the Bayesian outage model identified as slowest to recover, the percentage of households with reliable functional cooling is lower than the aggregate statistics suggest. Old units, insufficient capacity, leaking ductwork, inability to afford the electricity to run the system during a prolonged event. These are not edge cases. They are the norm in the communities where the deaths will be concentrated. And there is a fourth dimension the AC argument misses entirely: the people for whom air conditioning is structurally unavailable regardless of the grid's status. Outdoor workers, the construction crews building the data centers that are straining the grid, the farm workers harvesting crops in the Rio Grande Valley and the Mississippi Delta, the delivery drivers, the roofers, the road construction crews, the utility linemen who will be sent out to restore the power during the next compound event. These workers produce 300 to 500 watts of metabolic heat through physical labor, 4 to 6 times the resting rate. Their wet bulb threshold is lower than the Penn State Chamber subjects because the chamber subjects were performing minimal activity. A construction worker operating at moderate intensity in 95-degree heat with a dew point of 78 is already in the danger zone that the Vanos model identifies for sustained exertion. California's heat standard, the only state-level standard with teeth, enacted in 2005 after investigation, found 46 heat-related illness cases the prior year, including the death of Asuncion Valdivia, a 53-year-old farm worker who died after picking grapes for 10 hours in 105-degree heat, has been associated with a 30% drop in heat-related injuries. OSHA's proposed federal heat standard, published in August 2024, would be the first ever federal regulation specifically addressing workplace heat exposure. The informal public hearing concluded in July 2025. As of this recording, no final rule has been issued. 5 Gulf Coast states, Texas, Louisiana, Mississippi, Alabama, and Florida, have no state-level heat standard of their own. The AC argument is not wrong about the past. It is wrong about the future because it assumes a level of grid reliability, universal access, and indoor containment of the population that the evidence says we do not have and are not on track to achieve before the conditions arrive. So what is the honest synthesis? Adaptation works, genuinely, measurably, within the range where the body's cooling system is functional. Heat action plans save lives. Cooling centers save lives. Better building codes save lives. Urban tree canopy programs. Cool roof mandates. Early warning systems. All of these push the mortality curve downward. And they should be expanded, funded, and accelerated, but the adaptation curve is being outrun by the exposure curve. The wet bulb trend is steeper than the institutional response. The Penn State data moved the threshold 4 degrees closer to current conditions, and the planning documents have not been updated. The Vanos physiology model identified survivability limits for older adults that are already routinely exceeded in the Gulf Coast summer, and no federal heat standard has been finalized. The California heat standard, which works, which cut injuries 30%, covers 1 state. The 5 Gulf Coast states most exposed to humid heat have no equivalent, and the compound event, the one where heat and infrastructure failure arrive together, sits outside the planning framework entirely. No heat action plan I have reviewed for any Gulf Coast county includes a scenario in which a multi-day power outage coincides with wet bulb temperatures above 30 degrees Celsius. That scenario is not hypothetical. It is the operational description of what happened during Eta, Beryl, Irma, and Laura, and what the Gulf's warming trajectory and the grid's structural fragility make increasingly probable. The honest answer is that both things are true at once. The adaptation is real, and it is not enough, and we have to hold both of those for the rest of this investigation. Other nations have moved faster. Qatar bans outdoor work when the wet bulb globe temperature exceeds 32.1 degrees Celsius, 89.8 Fahrenheit. That is a hard regulatory threshold tied to the actual metric that determines physiological danger. It is not perfect. Human Rights Watch has documented gaps in enforcement, particularly for migrant laborers, but it is a framework built around the right number. The United States, as of this moment, has no equivalent, not at the federal level, not in any Gulf Coast state. The regulatory architecture treats heat as an occupational nuisance, not as the lethal thermodynamic boundary that the physiology says it is. Part 13, the timeline. I want to be careful here, because projections are not prophecy, and I do not want to present them as though they are. But I also need to tell you what the models show, because the models are telling us something about timing that matters for decisions being made right now. Colin Raymond's 2017 paper, Saporki, with Deeptai Singh and Radley Horton, mapped the spatiotemporal patterns of extreme wet bulb temperature across the contiguous United States. The Gulf Coast and Southeast were already the national hotspot. The wet bulb extremes clustered along the coastline, the same 10 to 20 kilometer coastal strip Raymond would later identify in his 2020 global study, and the synoptic conditions associated with these extremes, persistent high pressure ridging, southerly flow off warm Gulf waters, stagnant air masses, are the same conditions that the summer 2026 forecast is pointing toward. El-Fadi El-Tahir at MIT, who has done foundational work on wet bulb projections for the Persian Gulf and South Asia, has described the trajectory for coastal subtropical regions as one where the question shifts from "will this happen?" to "how often?" That framing is important because it changes the nature of the policy response. If the question is "will it happen?", you can study it. If the question is "how often?", you have to build for it, and the Gulf Coast has not built for it. Under current emission trajectories, the frequency of wet bulb temperatures exceeding 31 degrees, the PSU heat threshold for young, healthy adults, is projected to increase across the Gulf Coast, from a handful of events per decade to multiple events per summer within the next 10 to 15 years. For older adults, the threshold is already being routinely exceeded. The Vanos and J physiology model showed that their lower survivability bounds correspond to conditions that occur regularly in the southeastern United States during a normal July, not during a heat wave. During baseline summer weather, the threshold is not approaching for this population. It has arrived, and the El Niño question adds a layer of uncertainty that cuts in the wrong direction. IRE's spring 2026 models show the El Niño strengthening through the summer, with some ensemble members tracking toward a strong event by fall. If El Niño reaches Super El Niño territory, and several analysts, including the weather data team at weatheronthisday.com, have flagged this as a non-trivial possibility, global temperature records are likely to fall in late 2026, and especially in 2027. That would not just affect the Gulf Coast, it would affect every wet bulb hotspot on the planet simultaneously. The 2023 to 2024 El Niño cycle pushed global temperatures to their highest levels in the instrumental record. A stronger El Niño in 2026 to 2027 would start from that elevated baseline, and the Gulf of Mexico, already running at record SSTs, would be the thermal amplifier that converts a global signal into a regional catastrophe. The lesson from the 2023 to 2024 cycle is worth holding. That El Niño, which was moderate to strong, not extreme, delivered the hottest summer on record for Texas in 2023, the new all-time ERCOT demand record of 85,508 megawatts, and the conditions that fueled Hurricane Beryl's July 2024 rapid intensification in the Gulf. And 2024 was the warmest year on record for Texas overall, according to NOAA's annual climate summary, if a moderate to strong El Niño produced those outcomes. A strong to very strong event operating on top of an already warmer Gulf baseline does not simply scale linearly. The nonlinear relationships between SST and atmospheric moisture content, between moisture content and wet bulb temperature, between wet bulb temperature and human physiological failure mean that incremental warming in the forcing produces disproportionate increases in the outcome that matters, the frequency and duration of conditions above the threshold. The planning gap is this. Infrastructure built to handle events on a 30-year return period is now facing events on a 5-year cycle, and the cycle is accelerating. The wet bulb observations are arriving decades ahead of where the climate models said they would be. Raymond's own characterization of his 2020 findings was unambiguous. The most important takeaway is the steepness of the trends. It didn't matter what level of extremeness we looked at or what part of the world, the trends were upward across the board. Upward across the board, in every region, at every threshold, faster than the models predicted. The question of whether the United States will experience its first multi-day sustained wet bulb event above the Penn State threshold is not a question of if. The station data says the conditions have already occurred in short bursts, an hour, 2 hours, at individual coastal stations. The question is when those bursts extend to 6 hours, 12 hours, 24 hours, and whether, when they do, the people in the path will have access to the cooling infrastructure that is their only physiological defense. That is a question the next 3 months may begin to answer. Part 14, the manageable challenge. I owe you honesty, and honesty means presenting the interpretation I find least alarming with the same rigor I gave the data that alarmed me, because this interpretation is not wrong. It is fair, and it accounts for real evidence that should not be dismissed. The first version of the story goes like this. The wet bulb threshold is lower than previously assumed. That is settled. The trend in extreme humid heat is upward. That is also settled. But the United States is not Jacobabad. It is not Karachi. It is not a country where hundreds of millions of people have no access to reliable electricity and no public cooling infrastructure. The U.S. has spent the last 3 decades building exactly the kind of adaptive capacity that the debunking section acknowledged is real. ERCOT, for all its structural vulnerabilities, has added real capacity. The summer of 2023 to the second hottest Texas summer on record saw the grid deliver record demand without rotating blackouts. How? In significant part through the rapid addition of solar and battery storage. Between September 2022 and May 2023 alone, more than 4,000 megawatts of wind and solar capacity came online. Battery storage agreements through 2024 totaled 7,945 megawatts. Utility-scale batteries are now a meaningful resource during the critical evening peak, the hours between 8 and 9 p.m., when solar output drops and residential cooling demand remains high. Cities across the Gulf Coast are adopting heat action plans. Houston, after Hurricane Beryl, revised its emergency response protocols to explicitly address post-hurricane heat as a primary threat rather than a secondary concern. Phoenix, which is not a Gulf Coast city but leads the country in heat mitigation research, has deployed cool pavement coatings, expanded urban tree canopy programs, and built a network of cooling centers with extended hours tied to NWS heat risk alerts. And the NWS heat risk tool itself represents genuine progress. Developed in partnership with the CDC, piloted in California starting in 2013, expanded to the Western United States in 2017, and rolled out nationally in 2024. Heat risk provides a color-coded, number-based forecast that integrates public health data with temperature extremes. It does something the raw temperature forecast cannot. It tells you how far outside the norm the heat is for your specific location and time of year, and it accounts for cumulative impacts, including overnight temperatures. The purple level, the highest risk category, signals conditions where anyone could be affected, not just the vulnerable. When that purple shows up on the 7-day forecast map, it is designed to trigger action by emergency managers, hospitals, and public health agencies. The tool is not perfect. It is still classified as experimental. It does not directly incorporate wet bulb temperature as a reporting metric, but it represents an institutional recognition that heat is a primary hazard requiring dedicated forecasting infrastructure. A recognition that did not exist in most of the country before 2024. Building codes are improving, though slowly. The International Energy Conservation Code has tightened insulation and air sealing requirements in recent cycles, which reduces the rate at which exterior heat penetrates occupied spaces. New construction in the Gulf states is meaningfully better at managing heat gain than the housing stock that existed during the Chicago disaster. Cool roof standards, reflective exterior coatings, improved glazing on windows. These are incremental improvements, but they compound. A well-insulated new home in suburban Houston with a high-efficiency HVAC system and a reflective roof can maintain comfortable interior temperatures during a multi-day heat dome with significantly less energy draw than a 1970s-era apartment in the 3rd Ward. The problem is that the new construction is in the suburbs. The old construction is where the vulnerable population lives. And the 35-degree wet bulb threshold, the one the Penn State study showed is wrong for sustained exposure, may rarely be reached in the United States in the near term. The station data shows brief exceedances, an hour or two at a time, at scattered coastal locations. Multi-day sustained events at that level have not been observed on American soil. The science says they are coming, but coming is not here. And the lead time between where we are and where the worst case projections live may be sufficient for institutional adaptation to close the gap. If the investment happens, if the political will materializes, if the OSHA heat standard is finalized and enforced, if the planning documents are updated from 35 to 31, if the grid investment keeps pace with the demand growth. That is a lot of ifs, but the optimistic interpretation holds that the trajectory is positive and it points to real evidence to support the claim. Current heat-related deaths in the United States, while tragic and undercounted, remain below pandemic or major hurricane scale. NOAA and the CDC estimated roughly 1,220 heat-related deaths per year in recent years, a number that almost certainly underestimates the true toll since many heat deaths are attributed to heart failure or other proximate causes on death certificates. But even with significant undercounting, the scale is a public health problem, not a civilization scale threat. This interpretation says the trend is real, the risk is genuine, and the work is urgent. But we have time, we have tools, and the trajectory of adaptation is positive. I think this interpretation is defensible, and I think the next interpretation is more consistent with the weight of the evidence. Part 15, the convergence. The second interpretation is where the published literature most directly points, and I want to be precise about why. Start with the threshold. Kenny and Vecellio at Penn State established that uncompensable heat stress in young, healthy adults begins at approximately 31 degrees Celsius wet bulb in humid conditions. Vanos and Jay's physiology model extended that analysis to older adults and found survivability limits as low as 21.9 degrees under certain conditions. The population most exposed to Gulf Coast heat, elderly residents, people with cardiovascular disease, people on medications that impair thermoregulation, fall squarely into the demographic where the lower bounds apply. Those lower bounds correspond to conditions that occur regularly on the Gulf Coast during a normal summer, not during a heat wave, during baseline weather. Now add the trend. Raymond's analysis showed that extreme humid heat has more than doubled in frequency since 1979. His 2020 characterization, the most important takeaway, is the steepness of the trends, has been reinforced by every subsequent data update. The observations are arriving decades ahead of the climate model projections. When the models said mid-century, the station data said now. Now add the grid. The grid is real. The improvements are real. Battery storage is real. But the improvements are running to stay in place, not to get ahead. ERCOT's 2026 demand forecast, 92 gigawatts a year, represents a level of demand the system has never been asked to meet. The structural load growth from data centers and cryptocurrency mining is creating a permanent demand floor that compresses the reserve margins the system needs during peaks. And the ASCE's assessment, D+, requiring hundreds of billions in additional investment, DIR, was not a projection. It was a diagnosis of the system as it exists today. Now add the compound event. This is not theoretical. Since 2017, 4 U.S. hurricane landfalls have produced multiple heat-related deaths during post-storm power outages. Beryl, Irma, Laura, Ida. The pattern is established. The mechanism is understood. Michael Oppenheimer's compound risk framework. Consequences more severe than the sum. It describes exactly what these events produce. And the conditions that generate them, warm Gulf water, fueling both stronger hurricanes and higher wet bulb temperatures that are intensifying, not stabilizing. And the 2024 North American heat wave provides the most recent data on what even a non-compound heat event now costs in the United States. Over 1,000 heat-related deaths across the country, concentrated in the South and Southwest. That was a year with no major Gulf Coast hurricane heat compound event. The baseline death toll from heat alone, without the compounding factor of a post-hurricane blackout, already exceeds 1,000 annually. The convergence interpretation asks, what happens to that number when you add a multi-day power outage to a population already operating near the physiological edge? The convergence interpretation says the threshold is lower than planned for. The trend is steeper than modeled. The grid is more fragile than advertised. The compound event is not hypothetical. It has already killed people 4 times in the last 8 years. And the population in the danger zone is growing, aging, and increasingly dependent on a single point of failure: uninterrupted electricity. This interpretation does not say catastrophe is inevitable. It says we are not preparing fast enough for what the peer-reviewed data shows is coming within this decade, and the gap between the speed of the threat and the speed of the response is widening, not narrowing. Consider the timelines. The Penn State PSU heat findings were published in February of 2022. The Vanos and J physiology-based survivability model was published in November of 2023. The Vicelio-Pinas paper quantifying population-level risk enhancement was published in October of 2023. As of June 2026, more than 4 years after the PSU heat study, no federal, state, or local heat action plan in the Gulf Coast region has formally adopted the updated 31-degree threshold. The OSHA heat standard, proposed in August 2024, went through public hearings in the summer of 2025. The final rule has not been issued. The planning documents still reference 35 degrees, 4 years. The science moved, the policy did not. And every summer that passes without updating the framework is a summer where the assumptions guiding emergency response are calibrated against a number the evidence says is wrong. The convergence interpretation does not require a worst-case event to be validated. It is validated by the structural mismatch between what the science says and what the institutions are doing about it. The heat is accelerating. The adaptation is incremental. The gap is the risk. Part 16, the threshold decade. The third interpretation is the one I find most difficult to present because it requires me to follow the evidence to a conclusion that sounds extreme until you look at the numbers behind it. So I am going to present the numbers and I am going to let them do the work. The Gulf of Mexico is warming at 0.32 of a degree Celsius per decade over the past 30 years. Since 2012, the acceleration has been even steeper. Kim Wood's tracking data as of May 2026 shows SSTs tied with the warmest on record, and the warming is not confined to the surface. Brian McNulty's ocean heat content graphs show the thermal energy building through the full water column, a deep reservoir that does not dissipate between seasons. That deep warmth serves a dual function. It loads the atmosphere with moisture, the moisture that drives wet bulb temperatures toward the threshold along the coastal arc from Brownsville to Pensacola, and it fuels the storms that are the primary mechanism for removing the power grid from the equation. El Niño is building. If the models tracking toward a strong event in late 2026 are correct, the thermal baseline for the 2027 summer will be elevated further. The relationship between El Nino and Gulf Coast heat is not linear, it is amplificatory. El Nino does not simply add a degree to the baseline. It reshapes the atmospheric circulation pattern over the entire Gulf of Mexico region, favoring persistent ridging, persistent high pressure that suppresses convection, inhibits cloud formation, and creates the stagnant, moisture-laden air mass that is the precondition for extreme wet bulb events. The last time a strong El Nino coincided with record Gulf SSTs, 2023 into 2024. The result was a summer that shattered heat records across the South and Southeast, drove ERCOT to a new all-time demand peak, and set the stage for Hurricane Beryl's rapid intensification in early July. That El Nino cycle was moderate to strong. The models currently tracking for 2026 into 2027 show ensemble members reaching strong to very strong territory. If that materializes, the thermal loading on the Gulf and the atmospheric pattern over the coastal South will be operating at a level the modern observational record has not seen. And the Gulf, critically, does not need El Nino to be warm. It is already warm. El Nino adds thermal amplification on top of a trend that has been accelerating for a decade and a half independent of the ENSO cycle. The 2012 to 2025 warming rate, each by 16 times the long-term average suits, is a structural shift, not a cyclical fluctuation. El Nino makes it worse, but the underlying trajectory makes the problem permanent. Now consider what the Vanos and J physiology model actually says about older adults. Their survivability limits, the temperatures beyond which sustained exposure leads to organ failure, range from 21.9 to 33.7 degrees Celsius wet bulb. Those lower bounds are conditions that the Raymond Station data says already occur on the Gulf Coast. Not in a decade. Now. For older adults without reliable air conditioning, the threshold decade may have already begun, and the number of older adults in the Gulf Coast danger zone is growing. The census data shows the 65-plus population in Texas, Louisiana, Mississippi, Alabama, and Florida outpacing the national average growth rate for that demographic. Texas alone added over 300,000 residents aged 65 and older between 2020 and 2024. Florida's retirement-driven population growth continues to concentrate elderly residents in precisely the coastal counties most exposed to both hurricane risk and extreme humid heat. The population that is most physiologically vulnerable is the population that is growing fastest in the geography that is most thermally exposed. And these residents are not evenly distributed within the metro areas. They are concentrated in the older housing stock, the inland neighborhoods where the buildings are brick and concrete, where the tree canopy is thinnest, where the urban heat island effect adds 2 to 5 degrees to the overnight temperature relative to suburban areas. The same neighborhoods that Chicago taught us are the killing ground. So here's the third interpretation, stated plainly. A single multi-day power outage during a heat dome event over the Gulf Coast, whether triggered by a hurricane, by grid failure under extreme demand, or by a cascading infrastructure collapse, has the potential to produce a casualty count that exceeds any single natural disaster in modern American history. The conditions that would generate such an event exist today. The infrastructure to prevent it does not. The Chicago heat wave of 1995 killed 739 people in a city with lower baseline humidity than any Gulf Coast metro, in a week when the wet bulb temperature never approached the thresholds the PSU heat data identified. The Karachi heat wave of 2015 killed approximately 2,000 people in 3 days when prolonged power cuts removed air conditioning from a population with no alternative cooling. The European heat wave of 2003 killed 72,000 people across a continent that had never considered extreme heat a primary hazard. And it was a dry heat event where the body could still attempt to cool itself through sweating. A Gulf Coast compound event would combine the worst features of all three precedents: the prolonged nighttime heat and infrastructure failure of Chicago, the power outage and humidity of Karachi, and the institutional unpreparedness of France. the systemic failure to treat heat as a hazard requiring the same level of planning, resources, and urgency that the same geography devotes to hurricanes. And the scale of the exposed population is larger than any of those precedents. The Houston metro area alone, Harris, Fort Bend, Montgomery, Brazoria counties, contains over 7 million people. The New Orleans metro holds 1.3 million, the Mobile metro, 400,000, the Corpus Christi metro, 320,000. A single compound event spanning 2 or 3 of these metro areas simultaneously, which the geographic footprint of a heat dome easily supports, would place more people in acute wet bulb danger than the total population of Chicago in 1995. This interpretation says the question is not whether a mass casualty wet bulb event will occur in the United States. The question is when, and how many people the first one kills depends on decisions being made right now. About grid investment, about emergency planning, about who gets power restored first, about whether nursing homes are required to have heat resilience plans as robust as their hurricane plans, about whether the number on the planning documents is 35 degrees or 31. I cannot tell you which interpretation is correct. I can tell you what each one costs if it turns out to be wrong. Part 17. What we know and what we do not. I want to be precise about this because precision matters most when the stakes are highest. What we know, the 35 degrees Celsius wet bulb survivability threshold, the number that has driven climate risk assessment for 15 years, is empirically wrong. The Penn State Human Environmental Age Thresholds Project, using direct physiological measurement on human subjects for the first time in the history of heat science, established that uncompensable heat stress begins at approximately 31 degrees Celsius in humid conditions for young, healthy adults. The Vanos and J 2023 physiology-based model found survivability limits for older adults as low as 21.9 degrees, more than 13 degrees below the canonical threshold. This is settled science. It has been replicated. It has been extended. The Vecellio 2023 PNAS paper. Greatly enhanced risk to humans as a consequence of empirically determined lower moist heat stress tolerance. Quantified the population level implications. Humanity is more vulnerable to moist heat stress than previously proposed. The number is wrong, and the consequences of the error are not symmetrical. The error runs in one direction only toward underestimating the danger. What we know. Extreme humid heat is increasing in frequency, intensity, and duration, and the increase is steeper than climate models projected. Colin Raymond's 22-20 Science Advances paper, analyzing over 7,000 weather stations across the globe going back to 1979, found that extreme humid heat has more than doubled in frequency. The doubling was not gradual. It tracked with global mean temperature rise and with regional sea surface temperature anomalies. Over 250 readings above 33 degrees Celsius have been recorded globally, and the 35-degree theoretical ceiling has already been breached at 2 stations. In the United States, the Gulf Coast, New Orleans, Biloxi, coastal Texas, and Louisiana is the epicenter. These are not remote observation posts. They are metro area weather stations. What we know. The Gulf of Mexico is warming at a rate that has increased by a factor of 10 over the past 30 years relative to the long-term trend, with further acceleration since 2012. Sea surface temperatures as of May 2026 were tied for the warmest on record for the date, with deep ocean heat building through the water column, in a pattern that does not reset between seasons. This warming simultaneously feeds moisture into the atmosphere, driving wet bulb temperatures upward, and provides the thermal fuel for the hurricanes that destroy the cooling infrastructure the coastal population depends on. What we know. Compound events, hurricanes followed by heat waves occurring during power outages, have killed people in the United States 4 times since 2017. Beryl, Irma, Laura, Ida. The mechanism is established. The hurricane removes the grid, and the heat, which was survivable with ACE, becomes lethal without it. The pattern is recurring, and the 2025 projected increase in tropical cyclone-induced outage risk suggests it will recur more frequently, not less. What we do not know. the exact timing of the first sustained multi-day wet bulb event above 31 degrees on U.S. soil. The station data shows brief exceedances, an hour, 2 hours. The transition to 6-hour, 12-hour, and 24-hour sustained events has not yet been observed in the United States. When it occurs, depends on the intersection of several variables: Gulf, SST anomaly, atmospheric circulation pattern, El Niño state, and local meteorological conditions, whose interaction is difficult to project with precision. What we do not know, whether grid modernization, battery storage, demand response, renewable additions, state-funded generation use, will outpace the structural demand growth from data centers, cryptocurrency mining, and population increase in the Gulf states. ERCOT's 2026 forecast of 92 gigawatts of peak demand suggests the race is, at minimum, closer than the optimistic narrative implies. What we do not know, how the El Niño currently building in the equatorial Pacific will interact with the Gulf of Mexico SST anomalies to shape the 2026 and 2027 heat seasons. The models diverge on intensity. The range of outcomes, GAL, from moderate El Niño to a strong event rivaling 1997 and 2015, spans a difference of potentially several degrees in summer baseline temperatures across the Gulf Coast. The atmospheric pattern associated with a strong El Niño, enhanced ridging, persistent heat domes, suppressed convection, is the pattern most likely to produce multi-day wet bulb extremes. But the timing and geographic footprint of those extremes depend on the mesoscale details of atmospheric circulation that seasonal forecasts cannot resolve. What we do not know, whether the population's behavioral adaptation, the instinct to seek shade, drink water, check on neighbors, go to cooling centers, will scale to an event that exceeds what anyone in the current Gulf Coast population has experienced. Chicago taught us that behavioral adaptation fails when the event exceeds the population's mental model of what is possible. Chicagoans in 1995 did not go to cooling centers because most did not believe they were in danger. They had survived hot summers before. The heat wave that killed them was categorically different from anything in their experience, but it did not announce itself that way. It arrived as summer. It arrived as weather. And by the time people understood it was something else, 739 of them were dead. What would answer these questions? Continuous wet bulb monitoring at coastal weather stations, not just temperature and humidity reported separately, which requires the user to perform a calculation to derive the wet bulb value, but calculated wet bulb temperature as a standard reporting metric in the NWS Surface Observation Suite. This is technically trivial. The instruments are already reporting the inputs. The calculation is straightforward. But as of this recording, wet bulb temperature is not a standard element in the hourly METAR observations that forecasters, emergency managers, and the public rely on. It exists in research datasets. It exists in the heat risk tool's internal calculations. It does not exist as a number you can look up on the NWS station page the way you look up wind speed or visibility. Enhanced integration of NWS heat risk products with county emergency management activation thresholds, so that a purple heat risk day in Harris County automatically triggers cooling center activation, welfare checks on registered vulnerable residents, and pre-position EMS resources. Some jurisdictions have begun this integration. Most have not. Power outage data linked to real-time heat exposure assessments during and after tropical cyclone landfalls. When a hurricane hits the Gulf Coast in August, we know within hours how many customers have lost power. What we do not know, what nobody is systematically measuring, is the wet bulb temperature inside the blacked out homes in the outage zone. That gap between the outage data and the exposure data is the gap where people die without being counted until the medical examiner catches up weeks later. And perhaps most critically, the adoption of the updated physiological thresholds from the Penn State and Arizona State research into federal, state, and local heat action plans, replacing the 35-degree standard that the evidence has conclusively shown to be wrong. This is not a funding question. It is not a technology question. It is a decision. The science exists. The planning documents have not been updated to reflect it. That is a choice, and it has consequences measured in lives. You can track the data yourself. The NWS Experimental Heat Risk Tool is publicly available at heat.gov. NOAA's sea surface temperature products update daily. The Coral Reef Watch daily 5-kilometer product gives you Gulf SST at a glance. ERCOT's grid conditions dashboard shows real-time demand and reserve margins. Brian McNulty's ocean heat content graphs are updated regularly at his University of Miami research page. The instruments exist, the data products exist. The gap is between what the instruments are telling us and what the planning documents assume. Part 18, what we will be watching. This investigation began with a number, 95 degrees Fahrenheit, 35 degrees Celsius, the temperature that for 15 years has defined the boundary between survivable and unsurvivable heat. And the first thing this investigation found is that the number is wrong. The boundary is lower. It is 4 degrees lower for young, healthy people. It is potentially 13 degrees lower for elderly adults. The margin that everyone assumed existed, the safety buffer between where we are and where biology fails, was never as wide as the planning documents suggested. And it is narrowing every year at a rate that the observations say is steeper than what the models predicted. The second thing this investigation found is that the boundary matters most when the machine breaks. Not the heat alone. The heat arriving at the moment when the only system capable of holding the population below the threshold, the electrical grid powering the air conditioning, goes offline. That compound event is not a scenario. It has happened 4 times in 8 years. The geography where it happens, the Gulf Coast, is the same geography where the wet bulb trend is most aggressive. And the grid serving that geography just received a near-failing grade from the country's most comprehensive infrastructure assessment. I do not know which of the 3 interpretations will prove correct. I do not know whether this summer will be the summer that tests the threshold in a way we have not seen before, or whether that test is 5 years away or 10. But I know what the evidence says about the direction, and the evidence is not ambiguous. The trend is upward, across every metric, at every station, in every region that has the combination of heat and moisture that drives wet bulb temperatures toward the limit of what human bodies can survive. Colin Raymond said it most clearly. It did not matter what level of extremeness they looked at or what part of the world. The trends were upward across the board. This summer, I will be tracking 4 things: Gulf of Mexico, sea surface temperature anomalies through hurricane season, not just the surface number, but Brian McNulty's ocean heat content data that tells you how deep the warmth goes and how much fuel the water column is storing for the next storm. ERCOT reserve margins during the peak demand windows. The evening hours between 8 and 9 p.m. when solar generation drops off and battery storage and natural gas have to carry the full load alone. The hours when the grid is most vulnerable to a forced outage that could cascade. The NWS heat risk outlooks for the Gulf Coast, with particular attention to any multi-day purple scene, the highest risk category over metro areas, which would signal conditions where even healthy adults are at risk. And wet bulb temperature observations from the coastal stations that Raymond identified as the U.S. hotspots: New Orleans, Biloxi, Galveston, Corpus Christi, Mobile, Lake Charles, Pensacola. If the wet bulb readings at those stations start touching 31 degrees during a week when ERCOT is operating above 90 gigawatts and the Gulf is running 3 to 5 degrees above the baseline, that is the convergence. That is the scenario this investigation spent 2 hours building toward. And whether it happens this summer or next, or in 2028, the question that will determine the outcome is not a question about the atmosphere. The atmosphere is doing what the physics says it will do. It has been doing it measurably for 4 decades. The trends are upward across the board. The question is whether the systems designed to protect people from it, the grid, the emergency plans, the heat action protocols, the building codes, the federal heat standard that still has not been finalized, will be rebuilt to match the climate those people actually live in, rather than the climate those systems were designed for. Whether the number on the planning documents will be updated from 35 to 31. Whether nursing homes in hurricane zones will be required to maintain heat resilience plans as robust as their hurricane plans. Whether the people who restore power after a storm will be told which neighborhoods to reach first based on heat exposure data, not just infrastructure priority. These are not atmospheric questions. They are human questions, and the answers will be measured in lives. I will be watching. This channel will be here when the data moves. And if you have made it this far, 2 hours into an investigation about a thermometer wrapped in a wet cloth, then you are the kind of person who looks at the evidence before forming an opinion. That matters. It matters because every heat disaster in history, Chicago, Karachi, France, was preceded by the same silence. The data existed. The warnings existed. The scientific papers were published, and the institutions responsible for protecting people did not act on them until the bodies were counted and the investigation was underway. The data this time is clearer. The threshold is measured, not modeled. The trend is documented, not projected. The compound event is not theoretical. It has a body count. What remains is the question that has always separated the disasters that kill hundreds from the ones that are prevented. Whether the people with the authority to act do so before the event or after it. I do not know the answer to that question, but I know who is asking it, and I know that the asking, the paying attention, the following the data, the refusing to look away is the precondition for every answer worth having. We will be here.